All right, so last time we left off and we took a look at the measures, we calculated the measures of central tendency in this example here. And if you remember in this example here, we had to use the middle number when we plugged it into the calculator into list 1 for our incomes, and then the frequencies we just plugged into list 2, and we did one variable stats L1 comma L2 with the one mode, and with the other mode it was one variable stats L1, list L1 frequency list L2. Now, what you might have noticed about this example is that the vast majority, the biggest portion of people fell into these first couple of ranges here. So we have a lot of people in these first couple of ranges, and then as it gets to higher and higher values, the numbers sort of fade away. And that's a little bit different than the other example we see here, right? The highest frequency are in these middle values and they kind of fade away on both sides. But again, the frequencies in the income example, vast majority of people fall into those first couple of categories, and then it gets smaller from there. This brings us to looking at the idea of distribution shapes. And so basically, if we think back to the graphs and the data, our histogram can look a lot of different ways, but the shape of the distribution does mean something. And so we're going to look at a couple of different distribution shapes. Those distribution shapes are left skewed, right skewed, and symmetric. Now, when I say left skewed and right skewed, basically that means where the tail of the histogram is. So if there's a lot of data on the left and then the tail goes out on the right, well then it's right skewed. And what happens with right skewed data is that the median falls below the mean. In other words, the reason why we call this right skewed is because the average, the mean, is to the right of the median. So if we look at a couple of just basic examples here, right skewed data looks like there's a lot of data over here and then there's a tail on the right. And what would happen if you were actually following along on this is you would find out, let's see if I can highlight this. You would figure out that, I don't want that. The median might fall like right here, somewhere in that range, but the average would get pulled towards the right. So your average would be pulled towards the right of the median. And exactly the same thing happens in reverse with left skewed data. That the median would be somewhere over here and the average would have been pulled to the left. Now we saw this numerically as well once we went to the examples, the central tendency example we had earlier with the New Testament. We saw that the introduction of the New Testament took that average and increased it by a significant amount. Now, as far as symmetric distributions go, there's a lot of different ways that the symmetric distributions can look. I'm going to put the screen right there. So symmetric distributions can look a number of different ways. They can be flat, they can have humps in them, they can be all over the place. But the basic idea of a symmetric distribution is that there is some place on the distribution shape where I can draw a straight vertical line and have that distribution be symmetric, meaning that if I drew a straight line right here, oops, I can't draw a straight line very well. That's fine. Here, and I look to the right and I look to the left, they should be mirror images of one another. Same thing down here. If I look there, if I could draw a straight line to the right, to the left, they look like mirror images of each other. Now this last one, you can see the line is, here to here. So we see asymmetric distribution here. Now one thing I want to mention is that this distribution that sort of has the hump in the middle, that's called a bell-shaped distribution. It's also known as the normal distribution. So the bell-shaped distribution, normal distribution, that's where you have a hump in the middle, and then you have a tail on the right and a tail on the left. So a bell-shaped distribution, or the normal distribution, is what that looks like. And that's a distribution of data that we come by very often in nature and very often in statistics. In fact, we're going to look at that not just in this chapter, but a lot of chapter 7 and beyond is motivated by the bell-shaped distribution, by the normal distribution. So the bell-shaped distribution is very, very important. Now, what we're going to do is we're going to look at measures of variation. And when we talk about data, how you should think about this is that the central tendency tells us where the middle of the data is, so where the center of the data is. Variation, or all these other measures of variation, is going to tell us how spread out the data is. So when I say spread out, I mean sort of numerically. So if I just give you two sets of data, one is 64, 68, 68, and 72. It turns out that set 1 has a mean and a median, which are both 68. If I give you another set, 0, 60, 76, and 136, the mean and the median of that set is also 68. All right, so all means, or excuse me, both sets have means of 68, and both sets have medians of 68. But we can clearly see that set 1 is much less spread out than set 2. There's big gaps in the numbers of set 2 compared to set 1. And so that's what we mean by spread out. Gaps in the numbers are spread out. Another way to think of it is as being on a number line. If you drew it on a number line, where would, one point versus the next be? So we're going to develop basically a few measures of variation. The first one is probably the simplest one and also the one you've most likely seen before. It's called the range. And simply speaking, the range is the difference between the highest and the lowest value. So if I wanted to look at the range of these two sets, all I would do is take a look at the highest. So for set 1, I would take a look at the highest value, which is 72, and the lowest value, which is 64. And I would say, well, what is the distance between 72 and 64? And so that just requires me to subtract 72 minus 64 and say the range of set 1 is 8. Now in set 2, the highest number is 136, the lowest number is 0. So I would take 136 minus 0, and I would say the range is 136. So set 2 has a range of 136, whereas set 1 has a range of 8. Just as a little side note, oftentimes people will get thrown off by the distinction between mid-range and range. Mid-range is halfway between the lowest and highest point, so we have to add the numbers and divide by 2. Range is just the distance between the lowest and the highest. So they both deal with lowest and highest. One of them is halfway between, so we add them up and divide by 2. The other one is we just subtract. So range, we just subtract. Mid-range, we add them up divided by 2. So range is just simply distance between the highest and the lowest values. Now, one of the troubles with range is the same trouble with mid-range and with median. And that is that it doesn't take into account all of the values. It just looks at the highest and the lowest. So if we take a look at these two sets, 1 and then a bunch of 5s and then 10, and then 1 and then a 3, 4, 5, 6, 7 and then 10, these would have the same range. So the middle values don't have any impact on range. And so we want to develop a tool for measurement that measures how spread out a set is, but that also encompasses every value, just like the mean encompasses every value when we deal with central tendency. And the tool we use there is what's called standard deviation. Okay? Now, there's actually 2 ways to calculate standard deviation. The first one that I'm showing you is the standard deviation that we're going to use when we deal with a population. Now, this formula isn't one that you're going to have to memorize and repeat, but it is something that you're going to have to, match on a test. So I might have this in a matching section of a test, and I'd say, well, which one of these formulas is the standard deviation for a population? And we can match it there. So what it does is it takes the square root and it takes every single value that I have and it finds the difference between the value that I have and the average. And then it takes that difference and it squares it, adds all those up for every single value, and then divides by n. After that, square root, I already said square root of all that. Now, population standard deviation is denoted by another Greek letter. Notice that population mean was a Greek letter mu. And we see that again here, mu. Well, population standard deviation is the Greek letter sigma. It's the lowercase sigma. Okay, so the uppercase sigma stood for add a bunch of things up. Lowercase sigma is always going to stand for a population standard deviation. So it tells you how spread out your population is. Now, oftentimes, another measure of variation that's really intricately connected to standard deviation is what's called variance. And we can see the population variance in that second formula. Notice that it's denoted by the standard deviation squared because that's what it is. It's just the standard deviation squared. So if we were to calculate this, if we found the standard deviation and then I asked for variance, all you have to do is square the number and find the variance. In other words, if your standard deviation came out to be 5, then the variance would have been 25. If the standard deviation came out to be 7, then the variance would be 49. So just square what you have for standard deviation, and that gives you the variance. All right, so let me illustrate just with a very quick illustration of how you would calculate population standard deviation. You're not going to have to do this by hand. It turns out our calculator does a lot of this for us, and so you're not going to have to do this by hand, but you will. I do want you to understand sort of what's going on in both the numerical sense of how it's being calculated and also based on sort of what's going on in a more general sense. So if you remember, we dealt with a set which was 10, 12, 13, 18, 20. And we found the average of that set to be 14.6. Now let's assume that this set is a population, that it represents some population of 5 individuals or 5 measurements. If this is a population, then the way to do the standard deviation is to say, okay, the average of that set was 14.6. So what we're going to do is we're going to take 10 and we're going to subtract 14.6 and then square that number. And then we're going to go on to the next number. And we're going to take 12 minus 14.6 and square the number. And so on and so forth. And so, for instance, in this one, what you would do, 10 minus 14.6 becomes negative 4.6. All right? 12 minus 4.6 becomes a negative 2.6. 13 minus 14.6 becomes negative 1.6. 18 minus 14.6 becomes 3.4. So and 20 minus 14.6 becomes 5.4, right? And then what we would do is we would square each number, add them all up, and then divide by 5, and then take a square root. Okay, so that's how you would calculate. You would end up with about 3.77 as your answer. And by the way, if 3.77 is the standard deviation, we could square that number. So we have population standard deviation is 3.77. We could square that number, and we could get the population variance as 14.21. Again, I'm rounding things to 2 decimal places in both cases, right? So that's how it's done. Now, this kind of illustrates why the need for these squarings. These squarings, what they're going to do is they're going to make these negative numbers. Obviously, negative 4.6, 10 was 4.6 to the left of the average, 14.6. So it's going to take those negatives, and by squaring that, then all of these things become positive. All right. And so that's what's going on. So that's kind of the numerical way to see the standard deviation. But the more intuitive way is to think about standard deviation as being a distance. All right. So if you think about what a distance does, if we have the points 4, 6 and the point 5, 5, and I want to find the distance between those 2 points, how would I do that? All right, so this is how we'd do it. We'd say, well, 4, 6, let's just put a point on the graph right here. And then we'd say, well, 5, 5, let's put another point on the graph over here. Okay. And what you would do is you'd say, okay, the distance between them is this straight line. But what happens is that this straight line is a hypotenuse of some right triangle. Notice that the height of this right triangle is the difference between 5 and 6, and that the length of this base of the right triangle is just the difference between 4 and 5. So in other words, it's the difference between the y values, and this one is the differences between the x values. Okay? Which, again, we can find our distance by using the Pythagorean theorem. So here's what I'm saying, right? Pythagorean theorem is a squared plus b squared equals c squared. And what we found was that in our case, the a, let's say there was the differences between the x values, would have been 4 minus 5. And the b, which was the differences between the y values, would have been 6 minus 5. And in order to get the distance, again, our distance is our hypotenuse, which is c. And if we think about what that means, well, c squared is that. So what we could do is we could highlight this thing and try to square root the whole deal. Yep, good. So our distance is just the square root of differences between 4 and 5 squared and the difference between 6 and 5 squared. Notice how that matches very well with our general formula, with our general, we have a square root of a bunch of stuff squared. All of that stuff is coming from a difference of a value and an average, okay? The other thing you'll notice is that with the sets we had, 4, 6, if I think about that as having a two-value set, 4 and 6 has an average of 5. So what we really did there is we found the average of 4 and 6 being 5, and then the distance between our set or our point 4, 6 and the set which has values always just 5, the distance between those two sets would have been given to me by this. Now, there is a division by n that we do have to take into account when we deal with standard deviation, but that's just a factor, a limiting factor when you get more and more when you get bigger and bigger sets, that makes sure standard deviation not fly out of control in terms of size. So that's what standard deviation is. So standard deviation is the distance between our set and a set that it has all constants. All right, so like if our set was 4, 6, and the set of all constants would have been 5, 5. Okay, so what does standard deviation tell us in short? Well, standard deviation tells us how spread out our data is, and it tells us how far we are distance-wise from a constant set. All right. So yeah, that's what standard deviation is really, in fact, telling us. Now, here's the twist, plot twists, whatever, I don't know what to call it. Standard deviation for a population, what we did is we took the square root, all of those differences squared, and then we divided by n. It turns out when my set is a sample, what I have to do is I have to take the square root of all those things added together, but I have to divide by n minus 1 underneath the square root. So instead of dividing by the size of my set, I'm going to divide by 1 less than the size of my set. And the same thing is true for sample variance. Now I want you to just really quickly take a look at the notation. Standard deviation on a sample is always going to be denoted by S. All right, so we had for population, we always did sigma, which looks like a little round ball with a line coming out the top. For sample standard deviation, it's always going to be denoted by S. That's not just in this class, that's in statistics in general. Okay, and variance similarly is going to be denoted by S squared. Okay. Now let me just, again, numerically look at what the difference is. So we said if this set 10, 12, 13, 18, 20, if that were a population, we'd have to take all the differences, 10 minus 14.6 and then square it, 12 minus 14.6 and square it, add them all up, and then divide by 5. Well, if this set was a sample, we'd do the exact same thing on the top, but we would have had to have divided by 4. Now, we saw that if this were a population, the standard deviation would be 3.77. However, if this would have been a sample, it turns out that the sample standard deviation of this set is 4.22. Okay, and we could obviously square that and get 17.81 for our sample variance. All right. So that's the idea of, whoops, 17, I said 0.81. That's the idea of the difference. Now I want to just point out the difference. What is the difference? Well, sample standard deviation is a little bit higher, and that's on purpose. That's really what that n minus 1 is doing. What it's doing is it's giving you a little bit higher of a number. And the reason it wants to give you a little higher number is because of the idea of a sample maybe not representing your population perfectly. In other words, it's kind of like giving yourself a little bit of wiggle room. The technical term we use for that is you're adding or you're getting rid of 1 degree of freedom. Okay, so because there's an estimate in the formula, we get rid of 1 degree of freedom, and that gives ourselves a little bit of wiggle room when we talk about trying to project from a sample onto a population. Okay, so that's the main idea. Now, here's the nice thing. The nice thing is we have these big formulas, and while we don't have to have them memorized, we do have to understand like that these may come up on a matching portion of the test where you have to match sample standard deviation to the to the formula. You have to match population standard deviation to the formula. Maybe you have to match a mean to the formula. But as far as calculations go, when we get an example like the weights of people at the grocery store, we're not going to spend a lot of time, all day calculating out the standard deviation and this variance and things like that. We're going to turn back to our calculator, okay? And when we turn back to our calculator, what we do sequentially is the exact same thing we did when we were talking about central tendencies. So what we're going to do is we're going to take this data set and we're going to input it into one of our lists on our calculator. If you forgot how to do that, it's stat, edit, and then we input all of 20 of these data points into our calculator. So why don't you go ahead and do that? Stat, edit, input everything into list 1, and if you want, pause the video for that, and then we'll use that to calculate the range, the population standard deviation, and the population variance. That's what these symbols mean, right? Lowercase sigma is the population standard deviation. Sigma squared is the population variance. So hopefully you just did that, paused, put all your data into list 1. So once you've done that, so by the way, just as a refresher, hopefully we don't have to redo this a whole lot. Again, I hit the stat button right there in my calculator. I go to edit, hit enter, and then in the list 1 I have all of this data. Okay. And once I've done that, we'll go back to the exact same thing we did in finding central tendencies. So we go stat, scroll over to calculate, one variable stats. Again, there's 2 different operating systems. If you have this operating system that says one variable stats, we'll go and make sure we hit L1. Again, if you forgot how to do that, that's second and then the number 1. If you have the other operating system, list will be L1. And since this is not a frequency distribution, you just hit list L1. And then nothing should be in a frequency list. I should put nothing after L1 here. Hit enter. And you see we get the exact same display we had before, where our average was 161.45. And then you start moving down the line. If you move all the way down to the end, you can see a minimum and a maximum. You can also see are standard deviations. Now, the standard deviations, there are two of them. This one asks us for the population standard deviation. So it asks us for sigma, which is fine. We can find sigma. Sigma is right on our calculator, and hopefully you can see that for this example, the sigma on our calculator gave us 65.19. 65.19. All right. By the way, just as another side note, the label on this, if I talked about weights of people at the grocery store, I'd assume we were talking about pounds. So that first person weighed 157 pounds. The average of 161.45, that would also be in pounds, okay? And it turns out the standard deviation is also in pounds. So the standard deviation has the exact same label that the average does, that the original data came in, okay? By the way, same thing with range. Range, if you scroll down, how are we going to find the range? Well, in this case, the biggest number was 305, the smallest number was 38. So we just take 305 and subtract 38, which gives us a range, of 267. So the range is 267, all right? That would have also been in pounds too. By the way, the variance is not in pounds. It would be in square pounds. That's one of the reasons we don't use it a lot. But how we would find this? Well, our calculator doesn't give us a variance, but what we can do is we can take the standard deviation and we can just square it. So take 65.19, square that number, and what I got is 4,249.74. All right, so you don't have to do a whole lot of extra work. By the way, hopefully you noticed that the sigma shows up on your calculator. What's right next to it is just the letter X. That just means what is the standard deviation of X. They always put X as your variable in the calculator. So sigma of X, the population standard deviation, was 65.19. Now, if you would, I'd like you to try this next example on your own. The manuscript example that included the Greek New Testament. So push pause on the video, I'll give about 5 seconds, and then try to find the range. This time, we're assuming that this is a sample of ancient manuscripts. So we're going to use the letter S, meaning the sample standard deviation, and S squared, meaning the sample variance. So find the range, the sample standard deviation, and the sample variance of this example. If you've typed things in on your calculator right, then you should have gotten out an average, again, that matched our average from the previous example. This is our previous example, so if you scroll back up and looked at the central tendencies, you should have the same central tendencies that we had before. 567.4 was the average. And by the way, you can imagine how cumbersome it would be to take 567.4, subtract each number, square that thing, add them all up, right? That would get very, very difficult. It would have gotten very, very difficult on the previous example too. So standard deviation is a number of ancient manuscripts. If we're doing the sample standard deviation, it's 1768.28. Okay, and then I would have done the minimum, the maximum, So maximum is 5,600, the minimum is 0. So if I take 5,600 and subtract 0, that just comes out to 5,600. Okay. If we wanted to find the variance, we take 1768.28 and we square it. So 1768.28 and then square it. It comes out to some very, very big number. 3,126,814.16, which is, by the way, 3,126,814.16. So that's how we do standard deviations, both population standard deviations and sample standard deviations on our calculator. All right. Now, the things we're going to look at next, I think what I'm going to do is I'm going to put this in a separate video. This video is taking up plenty of time. So I'm going to look at I'll do this in the next video. We're going to talk about why we would care about how spread out a set is. Well, we care about it from just the general principle, like how spread out a set is, but I'll talk about more in detail about how we do that on the next video.